This video is part 2 of an introduction to functions. So in the last video we talked about the definition for a function. Now we'll talk about notation. So often the y variable is not written when we're writing a function in equation form, and instead it's replaced by the notation f of x. So again, when you read this f of x, this simply emphasizes the fact that y is a function of x. Now, if needed, f of x can always be replaced with y. So if you wanted to rewrite it as a y instead, or if you were graphing it or entering something into your graphing calculator, you can do that. But it's important to note that f is just the name of the function. F stands for function. If more than one function are written, sometimes you use different letters. It could be a G, or a P, or a J, or an H, or really any letter that you wish. It's also very important to remember that the letter f is not a variable and should never be treated as a variable. So many students commonly mistake this as f times x. It is not that. This is just notation that means that you are given a function. Now, one thing we often like to do is evaluate functions for particular input values. So here, given the function f of x is equal to 3x squared plus x minus 5, we're going to find the value of the function at -2, or f of -2. So all that means is we're going to plug in the input, which is x, as a -2, and then perform order of operations. So this is exactly how you are to display your work. F of -2 equals, substitute the -2 in everywhere you see x. It's important to use parentheses, especially if you have a negative. And then go ahead and do the order of operations. So in this case, f of -2 would be equal to 5. So therefore the value of the function at -2 is 5. We also say that the image of -2 is 5. 5 is the y value that corresponds with the x value of -2. Now, it's also important to talk about the domain of a function. So domain we talked about before is a set of all inputs. Now, when we talk about domain of a function, we're really referring to the largest set of real numbers that can serve as inputs for that function. Because normally the set of inputs is an infinite set, so we can't just list them out. Now, there are sometimes restrictions on the domain, and here are some examples on where we might see restrictions on domain in a pre-calculus course. The first restriction would be if there's a variable in a denominator. We don't want the denominator to be 0. If there's a variable in a radicand with an even index, we do not want the value of the entire radicand to be negative. If we have a logarithmic function, we do not want the argument to be 0 or negative. And for trig functions, there are different restrictions depending on what the trig functions are. So here we'll focus on more basic examples. We'll leave the logarithmic and trig functions for later on in the course. We'll look at the examples where we have polynomial functions, rational functions, and radical functions. So taking a look at number 1, we have f of x is equal to 3x plus 45. Number 2, g of x equals 3 minus x divided by 2x plus 10. And number 3, h of x is equal to the square root of 4 minus 2x. So take a moment and think about what the domain of these three functions should be. And remember, you're always starting with the real numbers, and then you're just going to delete any values that makes the expression or the function undefined. So take a moment and pause, and then I'll talk about these solutions. Alright, so let's take a look at the domain of these three functions. The first function that we were given was linear. F of x is equal to 3x plus 45. So here we didn't have any restrictions because there's no variable in the domain. There's no variable under a radical. So this is just a polynomial function. Therefore, the domain of this function would be all real numbers. It's also important to note that this is an increasing line. If you were to think about this in terms of the graph, the slope is positive. And we can write our domain in several ways. Here we're writing it in set notation at set of all x, such that x is a real number. You could also write that in interval notation. Number 2, our function is rational. G of x equals 3 minus x divided by 2x plus 10. So here we have a variable in a denominator. We want to make sure that that denominator is not equal to 0. So we can go ahead and solve this. And find out what x should not be equal to. So here we know x is not equal to negative 5, which means we're taking all real numbers but excluding when x is equal to negative 5. And again, in set notation, we have the set of all x such that x is a real number, but x is not equal to negative 5. And you could represent that in interval notation as well. Now number 3, we have an equation that contains a radical, a square root, so that has an even index. So here we do not want the radicand to be negative. So we'll set the radicand greater than or equal to 0 and then solve. Remember here that when you're dividing by a negative in an inequality, and of course I miswrote it as I'm saying it, but you should change the direction of the inequality symbol. So here x is less than or equal to positive 2. So that's our restriction on the domain. All the x values that we plug in have to be less than or equal to positive 2. So in set notation, we have the set of all x such that x is a real number, but x is less than or equal to positive 2. And once again, you could represent that as an interval. Right, the next thing we'll talk about in this video is arithmetic of functions. So we can form new functions by adding, subtracting, multiplying, and dividing other functions. And here's just the notation that you will see for each of those cases. So we have the sum of f plus g. These are just two functions. And if we were to write it using function notation, you might see it as we have on the left, or more useful, the way that you see it on the right. We take the first function, the expression for that function, and add it to the expression for the second function. Likewise, for the difference, f minus g of x, we could take f of x and then subtract g of x. For the product, f times g of x is equal to f of x times g of x, and you may or may not see the multiplication symbol. Now for the quotient, f divided by g of x, we could take f of x and divide it by g of x, but this is only defined when g of x is not equal to 0. Now speaking of when these functions are defined, there's a little more to the domain when we're looking at arithmetic of functions. Now for all four of the operations we just saw, sum, difference, product, and quotient, you find the domain by doing the following. The domain of f intersected with the domain of g. So again, this symbol means the intersection. Think of that as and or both. And that means both of the domains of f and g have to be satisfied at the same time. The only caveat is that for the quotient, remember that the function in the denominator can also not be 0. So we're going to look at that case because that is the toughest case to think about. So here in this example, we have two functions. F of x is equal to 4 divided by x plus 3, and g of x is equal to x divided by x minus 2. We're going to define the quotient f over g of x and state the domain. So if you want to take a moment and try this one on your own, and then come back and take a look at the solution just to see how you did. Okay, so let's take these two functions. Remember, we were finding the quotient f over g of x. So I'm just going to rewrite that as f of x divided by g of x, to remind myself how I should set this up. And then substitute the expression for each function. So f of x is 4 over x plus 3, and that goes over g of x, which is x over x minus 2. So notice we have a complex rational expression. So we can simplify that by taking the reciprocal of the denominator, x over x minus 2, and multiplying. When we do that, we have 4 times x minus 2 over x times x plus 3. Now I'm not going to multiply, I'm going to leave it in factored form because that will help me to find my domain. So once again, let's just write the quotient, which is 4 times x minus 2 divided by x times x plus 3. Now we're looking for the domain. So first we'll find the domain of f and the domain of g separately. Remembering we want to intersect those two domains once we find them. So for the domain of f, we know that x cannot be equal to negative 3, because that would make the denominator in f 0. For the domain of g, we know that x cannot be equal to positive 2, because that would make the denominator 0. Now, since g is the function in the denominator, we also have to worry about the fact that g of x itself cannot be equal to 0. So we have to find out when that can happen. Since g of x is a rational function, the only way that it will be 0 is if the numerator is 0, which in this case is x. So we know x cannot be 0. Now we are intersecting these three things. So once again, the domain of the quotient, f over g of x, is the set of all real numbers. And we want to exclude x is negative 3, so x is not negative 3, x is not equal to 2, and x is not equal to 0. But any other real number besides those three values would be fine. And of course, you would do a similar thing for the other four operations. You just don't have to worry about the denominators being 0, but you would find the domain of each function and intersect them. Remembering that you could always rewrite a domain as an interval instead of set notation. Alright, so I hope you enjoyed the second part of the introduction of functions. Stay tuned for more videos on functions in the future.